Hey everyone, so we're back for lecture 16, and today we're going to talk about nonlinear systems of difference equations. So last time or a couple lectures ago, we talked about nonlinear difference equations, and then last time we talked a lot about multivariate calculus. And so, why we did this, to be able to look at now systems of difference equations, because that'll be pretty useful to us. So, let's talk about it in the context of this example. So let's consider the following system with variables xk and yk, and we have these two coupled difference equations here that talk about how these guys update in time, where the time step is k. So first, let's think about how we can write this as a multivariate function. So let's define zk, which is a vector comprising x and y, and then we'll write the right-hand side of the equation as a function, because we know we'll need that to calculate things like the Jacobian and so on. Oh, hold on. I got a shadow. This is okay. Hopefully, yes. All right. Okay, so what should f be? We know f should be a function of z, and I guess f is also a vector, so it's going to be f1 and f2, but to put a fine point on it, z is going to be x and y. And just copying the function from above, this should look like 3/4 x minus 3/4 xy plus 1/4 and 1/2 y plus 3/4 xy. So this is what our f should be. And does it satisfy this condition here that z at time step k plus 1 should be f of zk? Sure it does, right? Because all I'm going to be plugging in is xk's and yk's for the x's and y's here. That's going to be zk. So no problems there at all. So point 2 is, how do we find fixed points for this system, or equilibria for this system? So we call z star a fixed point if it satisfies that the right-hand side of the equation doesn't change. So f of z star is equal to z star. So let's find the fixed points for these systems. So the equilibria for the system should now have an x and a y component. So we're looking for some z star, which is a vector, which is x star and y star. If it's okay with you, I'm not going to write a bunch of stars because that's going to get painful. So we want to solve the algebraic equations. X is equal to 3/4 x minus 3/4 xy plus 1/4, and y is equal to 1/2 y plus 3/4 xy. Right, exactly the same as what we did for scalar difference equations, right? So vector difference equations. We just set the left-hand side equal to x star in this case, or y star. So essentially saying that at time step k plus 1, you should be the same as you were at time step k for x's and y's. Okay, so how do we solve this? Maybe the second equation is easier, or like a little more tractable here. So let's look at that guy first. So this equation, let's see, if I multiply everything by 4, that might make our lives a lot easier. 4y, I guess we'll say, is equal to 2y plus 3xy. So 2y is equal to, or let's say minus 3xy. This is an equals, this is a minus, is equal to 0. And so I can factor out that y. So y times 2 minus 3x is equal to 0. So there's two ways I can make this second equation equal to 0. Either y is 0 or this term here is 0. So if y is equal to 0, make sure you can see. Yeah, okay. If y is equal to 0, then what must the first equation be? Then the first equation becomes x is equal to 3/4 x minus 0 plus 1/4. So I have 1/4 x is equal to 1/4, otherwise known as x is equal to 1, which says that z star should be 1, 0. Cool. Put that in a box. Now the second condition that we have that makes the second equation equal to 0 is that this term 2 minus 3x should be 0, which is equivalent to saying x should be 2/3. So if x is 2/3, then the first equation becomes what? So I have 2/3 is equal to 2/3 times 3/4 is 1/2 minus 1/2 y plus 1/4, otherwise known as minus 1/2 y is equal to 2/3 minus 3/4. What's that? Common denominator is 12, so 8 minus 9/12, so minus 1/12, which implies that y should be 1/6, right? Is that right? Yeah. So the equilibrium or fixed point in this case should be 2/3, 1/6. Okay, so these are the two fixed points for my system. So now that I've found these fixed points, and remember, okay, so let's like regroup here for a second. This is a nonlinear difference equation. And so we don't have a lot of stuff that we can do with this. If I want to start like trying to solve this, you know, writing a solution that doesn't depend on xk, but just depends on k, you know, what we've done previously for linear systems, that could be problematic. That could be extremely hard. I don't know how to start doing that. So I'm going to look for equilibria and I'm going to try and talk about their stability. That might be like the first thing that we can do, right? We said that that's the biggest tool that we have in our bag of tricks for just starting to deal with nonlinear systems. Great, so that's where we are right now. So we have two fixed points. Let's just look numerically at what happens when we plot these in MATLAB. So for the first fixed point, 1, 0, if we start close to it, then what happens if I run this iteration for 20 time steps? So I'm going to start at an initial condition of 1.01 instead of 1, 0, right? There's a typo in my notes, but there's not in the one that I uploaded. So you'll see the right ones on your PDF if you are looking at the blank PDF and following along. And here's a plot. So on the PDF of the plot, you'll see there's colors on here, but you have what I think a blue square down here. This is right by the fixed point. The fixed point is at 1, 0, right? That's Z star here. A little bit above it is the blue square. That's our initial condition. And then we go to the 20th step of the iteration, that's Z20. Sorry, that's a little small for y'all, but hopefully you can see it on your PDF. So the circles are the ZKs, just for any ZK. The square is Z1, and the red star, which is here, is at time step 20. So you travel along here, increasing in time that way. So what's happening? You started close to the equilibrium, and you're moving away from it. So what can you conclude? Looks unstable, right? We're going to try and use the machinery that we built last time studying multivariate calculus to prove that. That's where we're going towards in this lecture. But just numerically, or not even numerically, if you just like did this by hand and cranked out a few terms, it's not looking stable, right? So let's look at the other fixed point. Remember, the fixed point is 2/3, 1/6. And so if I want to start like looking in the graph, so this is, let's say we started at 1/2, 1/3. So we started here. This is our Z1. And the equilibrium that we're looking for is 2/3, like so 0.66, and then 1/6, like 0.16. So something like here, right? This is where Z star actually is. So I started here, actually kind of far away, right? As compared to the other one where it was 1, 0, I started at 1.01. Now I'm starting at 1/2 as compared to 0.6, and 1/3 as compared to 0.1667. But as time goes forward, I'm going to go here until the red star is here. So this is where it's kind of hard to see it in black and white, but that's where Z20 is. So time moves this way. So what can you conclude from this picture? This looks asymptotically stable. Oh, maybe I should say, I mean, the axes are labeled, but these plots are X versus Y, right? Because I have 2D state in the system, so I have a 2D initial condition, and then I go forward in time. That's why there's not a time axis on here. So I'm having to draw the little arrow for time. But as I go forward in time, it looks like I'm approaching this fixed point, right? So this looks asymptotically stable. I hope these plots make sense. So 2D plots, and I'm going forward in time. I have Z, I start with, Z1, and then I go forward, or I guess I wrote Z1, but it's really Z not the way we usually write it. I use the iteration to find Z1, Z2, Z3. All these are 2D vectors, and I plot them here on a 2D plane, X versus Y. So each point is for a different K, so 0, 1, 2, 3, and so on, until I get to Z20. And then I look at the relationship between that progression in time and the equilibrium. This example seems to approach the equilibrium fixed point. This example seems to leave it. So what does this mean? Like, how can I kind of understand this? Let's remember what the discrete time update should look like, right? So if I start with just the first step, let's just start by writing out the first couple of steps. So let's just choose some Z naught close to our equilibrium. That's what we did, right? Why? Because stuff looks like it might be asymptotically stable. We know that you have to start close even for that definition, right? You can't just start anywhere necessarily. So what's Z1? Z1 is F of Z naught. Fine. I can add and subtract the equilibrium. That's totally kosher. So I have Z naught minus Z star plus Z star. This is a little trick we did last time, right? What I can think of, if I started close, I can think of this difference here as being small. So this is like a quantity in linear approximations that we would typically call H, right? And this is what we may call A. And so in that Taylor series or linear approximation notation, this is really F of A, or Z star, we say A, plus what? Plus the Jacobian at that point times this small number, this difference, right? This is just the first two terms of the Taylor expansion. Z naught minus Z star. So minus sign here. This is first two terms of Taylor expansion. Fine, but I know what this is, right? Since z star is in equilibrium, this is f of z star is just z star. This is equal to z star plus the Jacobian evaluated at z star times the initial condition minus z star. Okay, hopefully that seems fair. That's what we did last time, right? We started looking at that last time. So that's what the first step should be. What about the second step? Can we always have it in terms of the stuff that we know, which is our initial condition and our equilibrium? And of course, the Jacobian, it comes from knowing what the function is, right? So let's see, what's Z2? Z2 is just f of Z1. What's Z1? I can use this approximation here. This is f of, I'm writing approximately, right? Z star plus the Jacobian Z star, Z naught minus Z star. So I can again do a linear approximation here, and we have to close that. And the reason is this is small, and so this is small here, right? So let's just think of all of this as H, and this again as A. So the approximation of this is again f of z star plus, so I want the Jacobian times this h, right? The Jacobian at z star times the Jacobian at z star, z naught minus z star. Well, that's just the Jacobian squared, right? So this equals f at z star again is just z star because z star is a fixed point. The Jacobian at z star squared, z naught, oops, minus z star. And now you can see a pattern, right? So now I'm able to write the second step in my iteration without any z1s, right? It only depends on our equilibrium and on our initial condition and on our Jacobian. And so hopefully this pattern is kind of clear now. So I can continue this process. And if I want the kth step for z, this is just going to be z star plus the Jacobian at z star to the k times z naught minus z star. So it still depends on how far you're starting from the equilibrium initially. So that's very telling, right? I mean, so this is a linear approximation that we've done to fully understand the behavior that's local to the equilibria for a nonlinear system. So of course, it's not telling us about all these fun nonlinear stuff that we may be able to see, like, you know, chaos that we saw numerically, but we know locally at least what's happening near the fixed points, because this is a linear system, right? And we already know exactly what we need to do to understand this fully, right? What do we need to do? We need to find the eigenvalues of the Jacobian. Everything is determined by the eigenvalues of this, right? This is back to, like, you know, the last month of our class. We've been looking at systems that look like this with the matrix A, right? Jacobian is just a matrix. What do I care about? I just care about whether the spectral radius of this matrix is less than 1 or not. And so if the spectral radius of the Jacobian is less than 1, then the Jacobian to the k goes to 0, and z to the k, oops, sorry, zk. not z to the k, goes to z star. So that's the feeling that we have. We're going to have a theorem that actually says this, but it builds directly from what we did last class, finding approximations for the nonlinear systems, right? Nonlinear multivariate systems, and then all the stuff that we've done for linear systems so far. So hopefully that's very clear. So let's go through a definition and a theorem that will help us formalize this. Okay. Here we go. So make sure see this. So suppose that we have a function and it has to be continuously differentiable. So that means that it's differentiable and the derivative is continuous. So everything has to be like sufficiently well behaved. So we say that a fixed point is asymptotically stable. So this z star is an asymptotically stable fixed point of the difference equation zk plus 1 is equal to f zk if there exists an epsilon greater than 0 such that for any starting value z naught that is within a ball of radius epsilon of the equilibrium, we have that as k goes to infinity, zk goes to z. So start close. We said stability is start close, stay close. Start close implies approach. Not just stay close, but that you go to it in the limit. Zk goes to z star in the limit. So that's asymptotic stability, exactly the same as linear systems, but you know, we have a norm, right? That's it. So here's the theorem. Suppose that our function, again, has to be continuously differentiable, and we have a fixed point of the difference equation. The fixed point of this difference equation, oh, I'm missing a word, is asymptotically stable if, and I wrote this on the last page, so by rho I mean the spectral radius. I'll put it here in case anyone has been asleep. So the spectral radius, the magnitude of the largest magnitude of the eigenvalues, right? The spectral radius of the Jacobian of f at the fixed point is less than 1. Then we have asymptotic stability. If it is greater than 1, then we have instability. So we're not going to talk about when it's equal to 1 in this class. That's inconclusive according to the results of this theorem. But this should be not super surprising. This is just based on what we did the last time. And in fact, the proof idea really follows it. Just follow the steps. So first, let's just consider the first result. So that's the asymptotic stability. And then we'll talk after. Once we see the proof of this, it's very clear where we get the unstable part. So let's suppose we have a function f, continuously differentiable, fixed point, fine. And suppose that the spectral radius of the Jacobian at the equilibrium is less than 1. So consider some initial condition so that we're start off close. So if we use a linear approximation, then this is the same calculation we did before. Z1 is f of z naught. You can add and subtract z star, approximate it using the Jacobian, and then note that f of z star is just z star. And we can do this approximation because this is small, right? That's why we need this step to say that z naught minus z star is small. Since the Jacobian is less than 1, we have that the Jacobian times this is small, right? Small number times some other kind of small number is also small, so we can do the linear approximation again. And that's what we did just previously. So z2 is f of z1, I plug this guy in, I do the same approximation, I get z star is the Jacobian squared, z naught plus, minus z star. If I continue this, I find the same iteration that we just found, that zk is approximated well by z star plus the Jacobian to the k, z naught minus z star. And so since the spectral radius is less than 1 of the Jacobian, we know that the limit of zk as k goes to infinity is just z star plus the limit of whatever this chunk is, and this decays. So Z naught is asymptotically stable, right? Because the whole thing approaches Z star. Everything would be fine, except for the instability, except now this term is going to blow up. And so we're not going to approach Z star. We're going to approach Z star plus some other junk. I don't know what it is. And that junk actually is going to go to infinity as k goes to infinity. And so that's how we get instability. We'll get some arbitrarily large number, or let's say arbitrarily large vector, or get arbitrarily far away from the equilibrium that we might have started nearby. So that's the big result from here. Should be pretty clear with what we've done for scalar systems and then also for multivariate systems. I'm going to stop it now and we'll go on to the next video just so it's not so long to upload. See you in a second.